Hey AP Stat students, this is Mrs. Brookshire. This is the last video of Chapter 7. This is 7.3, actually distribution of a difference between two means. And you see the homework there at the top. So what we're going to be talking about in the rest of this section is the sampling distribution of a difference between two means. In the preceding section, we developed methods for comparing two proportions. That was in 7.2. Remember how we had if we wanted to compare two proportions, we compared their differences? What if we want to compare the mean of some quantitative variable for the individuals in population 1 and population 2, such as the mean income for high school graduates and non-high school graduates? Our parameters of interest are the population means, mu1 and mu2. Once again, the best approach is to take independent random samples from each population and to compare the sample means, x bar 1 and x bar 2. We compare the populations or treatments by doing inference about the difference mu1 minus mu2 between the parameters. The statistic that estimates the difference is the difference between the two sample means. So it's kind of similar to comparing the two population proportions or sample proportions. So here's an example. To explore the sampling distribution x1 minus x2, let's start with two normally distributed populations having known means and standard deviations. Based on information from the U.S. National Health and Nutrition Examination Survey, the heights of 10-year-old girls and 10-year-old boys can be modeled by a normal distribution. The table summarizes this information. Suppose we take independent simple random samples of 12 girls, so that's your N1, and 8 boys, that's your N2, of this age and measure their heights. What can we say about their difference of x bar g, which means the mean of the girls, sample mean of the girls minus the sample mean of the boys, and the average heights of the samples of the boys and the girls? Okay, so this is the information that we know. For 10-year-old girls, we have an approximately normal shape. Here's the mean height. Here's the standard deviation. For 10-year-old boys, approximately normal. Here's their mean height. Here's their mean shape, or standard deviation. All right, so let's talk about the girls first. So shape, okay, approximately normal because the population is normal. So they're talking about this is the sampling distribution. We're coming up with the information for the sampling distribution of girls and then for boys. And don't forget, if the population is normal, then the sample is also normal. How do you find the mean? Remember, the mean of the sample is going to be the same as the mean of the population. And how do you find the standard deviation? First of all, check your 10% rule. So 10 times the number of girls in the sample, which was 12, is 120, is definitely going to be less than all 10-year-old girls. And to find the standard deviation, it's the standard deviation of the girls divided by the standard deviation of the number of girls in your sample, so we get a 0.78. So I'm going to give you a moment, take a minute and copy that down. So basically it's the same thing that we just covered when we did 7.3 part 1, okay? So the shape, don't forget, in a mean, the way you show normal is if the population is normal, then so is the sampling distribution. The other way was the CLT, if you central limit theorem. And remember, you can only use these two methods to show normalcy and means. You can't use it in a proportion. In proportions, you have to do the formula. N times P is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10. Okay, now let's talk about the sampling distribution of the boys. It's also approximately normal because the population is normal. The mean of the sampling distributions is going to be the same as the mean of the population of boys. And the mean height was 5.7. You do want to do the 10% rule, and it checks. So to find the standard deviation of the sampling distribution of the boys, you're going to take the population, which is the standard deviation of the population, which is 3.8, divide by, and the boys sample, there were 8. So that gives you that. Okay, so this is just kind of a review. Now what we're going to do is we're going to compare the two. Okay, so What we have here is, if you look at this diagram, this is 1,000 simple random samples of comparing girls and boys. Okay, we're going to do that here in this table in just a minute. When you do a difference sampling means, you want to choose a simple random sample. They don't have to be the same size. We saw they weren't here, of N1 from population 1 and N2 from population 2. And having that mean and standard deviation. And then population 2 has its own mean and standard deviation. So the sampling distribution of the difference is normal if both populations are normal. So both populations you can say are normal, then so is the difference. So you can either use the CLT if necessary, okay, or if you already know that the populations are normal, so are the samples. The mean of the difference is going to be just the mean of the population, the difference of the population means. And then the standard deviation here is the formula for that. So you square the standard deviation divided by N1, plus you square the second one divided by N2, and then you add and take the square root. You do need to check for the 10% rule. Again, on the formula sheet, here are those formulas. So here's how to, if you're doing the difference of two populations, that's easy enough. And then here's your standard deviation formula. Okay? So those are on the formula sheet. All right, now we're going to go through and we're going to do the sampling distribution of, we're going to do the difference of the means. That's what this whole thing is about. Using the given data from the previous problem, we're going to go through and we're going to state what the shape is, the center, and the spread. All right, so the shape. We can say that the shape of the difference is approximately normal because the mean we know of the sample mean of the girls and the sample mean of the boys are approximately normal. So if the populations are normal, so are the sample means. So they both have to be normal, and they are for that reason. We could say since both populations are normal. All right, center would be our normal. The center is going to be your mean, our normal. So what we're going to do is we're going to do x bar g minus x bar. The difference of the means is equal to the mean of the girls minus the mean of the boys. And so that would be 56.4 minus 55.7, which gives us 0.7. In the spread, they're talking about the standard deviation. So we do need to check that 10 times is less than the population. And we already did this actually before. If you look back at our first page, we said that these were both met, both of those conditions. So the way we're going to find the standard deviation for the mean difference is, if you look at the formula, it says to find the standard deviation of the girl, square it, divide it by the number of girls, and then the standard deviation of the boy, square, divide it by the number of boys. So when we go look at those numbers, the standard deviation of the girls' population was 2.7, the sample size was 12, and this was 3.8, and the sample size was 8, And that would give us a 0.155. 1.55. 1.55. And let's interpret this. Okay, so if we do an interpretation of the difference of the standard deviation, the difference, and then we're going to say, because we did girls minus boys, in the sample, the difference in the sample mean heights typically varies by 1.55 inches from the true difference mean height of 0.7 inches. Oh, goodness gracious, I'm sorry. So the difference between girls and boys in the sample mean heights typically varies by 1.55 inches from the true difference mean heights of 0.7. So that's what that standard deviation means. Is the difference is typically going to be about 1.55 from the true difference means, if they ask you to interpret. Okay, I think what we have left to do is a couple more examples. This one actually just, you can kind of read through this. It just talks about where do the formulas for mean and standard deviation come from. And it all goes back to chapter 6 with the random variables and just doing some substitution. And that is how we can come up with these formulas. So you can kind of look through that. And what we're going to do next, we had a problem here about a fast food restaurant using an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink amounts, or cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid L dispensed by the machine follows a normal distribution with a mean of 27, standard deviation of 0.8. When the medium set is chosen, the amount of liquid M dispensed follows a normal distribution. There's the mean, the standard deviation. To test this claim, the manager selects independent random samples of 20 cups filled using the large setting and 25 with the medium. So we're going to let X bar L minus X bar M be the difference in the sample mean of the liquids. What is the shape of the distribution? Find the mean, find the standard deviation, and then we're actually going to estimate a probability. Okay, so let's start off with A. What is the shape and why? So part A, what is the shape? Well, it does say that both populations, when you read through this, they both have a normal distribution. They both do. Both populations do. So we're going to say that the shape of the difference is normal because both populations are a normal distribution or normal distributions. So we know they're normal because of that. We don't have to do any kind of formula. We can just say they're normal because both populations are normal distributions. All right, I'm going to go jot some stuff down right here. Let's go write down some information. We got a large and we have a medium. So in the large, it says that the mean of the large is 27. The standard deviation of the large is 0.8. And the sample size, I think they said they were going to do for the first one, was 20. So okay. And then for the medium, and this is just going to help us as we're going to go through and work this problem out. So in the medium, the mean of the medium was 17. The standard deviation of the medium was 0.5 and 25 is what they're doing here. So the number in the sample of the medium was 25. Okay, so we did part A, part B. Find the mean of the sampling distribution. So again, we are doing the difference. So the mean of x bar L minus x bar M is equal to basically the mean of the large cup minus the mean of the medium cup, which is 27 minus 17, which is 10. So there's our mean. Okay, the next one says calculate and interpret the standard deviation, verify the 10% condition is met. So let's do the verification of the 10% condition. So 10 times the number in the sample of large has to be less than the actual population of the large. So 10 times 20, which is 200, is going to be less than or equal to all large cups, right? All large cups. Then we also need to meet that condition for the medium. So the medium cups has to be less than or equal to the population. So that's 10 times 25, which is 250, and that's going to be less than or equal to all medium cups, like the number. Okay, so once we have those conditions met, which we have, we can go over here and we can find the standard deviation of the large minus the medium. And that formula was to square the standard deviation of the large and divide by the number in the sample, plus square the standard deviation of the medium and divide by the number in the sample. So when you go through and you do the math here, you're going to end up with this equal to 0.205. So I would do, you either need to, it's up to you. I would probably do all of this first and then go take the square root of it. Or you could do it all at once. You may have to use some parentheses. Okay, it does tell us to interpret. So let's interpret this. So this is our standard deviation, 0.205. So we would say the difference, and we are doing large minus medium, so let's write that down. The difference in the sample mean, amounts of liquid, that's what this is, amounts of liquid, varies by 0.205 ounces from the true mean difference of 10 ounces. Okay, so the liquid, the mean is 10, but it could be different by 0.205. Okay, last question. Estimate the probability that the difference in the sample means is within 0.25 ounces of the true mean difference. Okay, within means it could be either way. So either way, 0.25. So if you have 10, 0.25, 10 minus 0.25 is 0.75. And we're trying to find that the mean difference, and then the other way would be 10.25. So within 0.25, so it could go either direction. So we could draw us a little diagram here. Mean is 10, and then over here we have 9.75, and then here we have 10.25. So this is the area that we're trying to figure. That's going to give us the probability. So we're going to have norm, CDF. We do know this is a normal distribution. We said that in part A. 9.75 is your lower bound, 10.25 is your upper bound, 10, and then 0.205. So this is our lower bound, this is our upper bound, this is our mean, and this is our standard deviation. And when we find that probability, it's 0.7774. So that would be the probability that the difference in the sample means is within 0.25 ounces. So the probability that your medium amount of liquid and large amount of liquid is between these two is 0.7774. All right. I think we have, that was the final answer, okay, or the final example here. So hopefully you guys feel comfortable with showing how you have normalcy. Don't forget, if you don't have a normal distribution, another way you could show normalcy is by the CLT, and you have to have your n's greater than or equal to 30, okay? So here we were told the populations were normal. We know how to find the mean, do your 10% condition, find your standard deviation, interpretation, and then find your probability. Okay, knowing that it's normal allows us to use this normal CDF. Okay, the last page, you are basically just copying some, filling in the blank. This is a summary for, so stop this if you need to. This is just a summary of everything that we've done in section 7.3. So take a minute and just pause this and copy these notes and make sure you feel comfortable with that. And then the last thing I did want to say, so pause this if you need to or go back to it. Here's your notation that we were talking about earlier, how you need to make sure that you feel confident in these symbols. So capital N is number in the population, little n is number in the sample. I think y'all are good. This is the population mean. This is the standard deviation of the population. This is the population proportion. P hat is the sample proportion. X bar is the sample mean. This is the mean of the sample proportions. And this is the mean of the sample means. So if you did all, remember, if you did all the proportions, you calculated the mean of all the proportions, then that's what this is. And this is the mean of the sample means. And then this is the standard deviation of the sample proportion and standard deviation of the sample means. How do you show independence? You have to do this before you can calculate the standard deviation on both proportions and means. If you have a proportion, this is how you show normal. And if you have a sample means, this is how you show normal. So that's different, these two things. So kind of jot those down. And that is the end of chapter 7.